Now, for dot products, is the math new? Yes, very new. You're not foiling, right? The math is very new. You're not foiling. However, even though you're not foiling, it's not hard as long as you just force yourself to get used to it, memorize it, and be able to do it. So what we saw on Friday is whether you have vectors in linear combination forms or component forms, either way, you're multiplying the x's, the coefficients, 4 times 1 or 4 times 1, plus you're multiplying the b coefficients or the vertical components, so -2 times -1, -2 times -1, you're just adding them together. It's a number, no big deal. Now, if you have a longer expression, just kind of do PEMDAS. Do a dot product of one, dot product of the other, put it all together. There are some fun formulas. But what we didn't get to finish on Friday is how to use the dot product. There are all these, not all these. What do we have, 2 or 3? I think there are 3 different formulas specifically that we're going to see in physics that use the dot product. So remember, pre-calculus is pre-everything future math, right? So I'm just kind of showing you the foundation to some formulas in physics and being like, hey, the dot product, it's a thing. I'm going to kind of explain what it's used for. I'm not going to necessarily go deep into the theory as to exactly why it's useful or how it's useful, beyond the fact that there are these formulas that need it. And so let's just get a little bit better at plugging into formulas with harder formulas that require a little bit more advanced math. Now that we've learned the dot product, let's use it, first of all, to solve for the angle between. So you have 2 vectors working completely against each other. Not even against each other. They just haven't been rearranged in a nice vector diagram. Is there a way to find the angle between? And the answer is yes. But I couldn't show it to you in section 6.3 because you needed the dot product first. So application of the dot product. There's this nifty formula. Some of you guys are getting it down because this was the very end of class on Friday. Long story short, can we use the formula and can we use it appropriately now that we know what a dot product is and we also know what magnitudes are? And hopefully with our trig, we know we need to do cosine inverse to get to theta itself. Our goal, solve for the angle between vectors. How are we going to do it? Using this new formula. Cosine of theta is equal to the dot product of 2 vectors, u and v, all over the magnitude of u, magnitude of v. Solves for the angle between in standard position with no transformation, no translation, no vector diagram. But this picture does actually show you something really interesting. If you connect 2 vectors head to head, you guys might want to grab out a color pen or highlighter and just make note of this. We haven't made a big deal of it because we were always doing vector addition. U plus v or v plus u, in which case we would want to flow through the 2 vectors. So we would move this guy up and we would flow through to get the resultant. But that's the addition. Technically, from head to head, that's the subtraction. From head to head, that's the subtraction. But if you guys notice, the order is important because addition, u plus v is v plus u. No big deal, right? But subtraction, is the same thing true? Is u minus v the same thing as v minus u? No. So, if you are making a quick note of joining 2 vectors head to head, this isn't specifically the point of this page at all, but it is an interesting note in physics. If you connect from head to head, you're going to end up with the subtraction of, in a sense, the terminal minus the initial. The terminal but not in the same way we did it before as far as one point minus another point, but the terminal, technically the terminal vector minus the initial vector. In your drawing of the vector, of the subtraction, where are you ending? Which vector are you ending at? Minus what vector did you begin at? Anyway, connecting head to head actually gives you vector subtraction, which is interesting. But, sorry, that's not the point. The point is how to find the angle between. Now the spacing is a little bit awkward. Lo siento. Every time there's an update to SMART, it ends up throwing all my spacing off. Let me make it all nice and pretty. But long story short, down here, number 32, you guys get two vectors, both in, what form is this called with the side carets? Good, component form. You have these two vectors in component form, and they say, find the angle between. All right, cool beans. Isn't there a formula for that? So let's go ahead and use it. All right, cool kids, applying the formula. What do we got? Cosine of theta is equal to, ooh, what do we need? First thing, don't we need the dot product? All right, what's the dot product of this guy? 12. Ooh, okay, hold on. Has the weekend been too long? All right. In order to plug into this formula, we need a dot product. Dot product says take the first, multiply, plus take the seconds, multiply. So what's 3 times 4? 12. And what's 2 times 0? 0. Is that okay? I'm just doing a dot product. And 12 plus 0 equals? All right. But we have to also review, who are these guys with the double lines on either side? Magnitudes. Okay. Review. How do we do magnitudes? Good. Which, Adam, what's another way of describing that formula to me? What is the square root of a squared plus b squared? What formula is that founded on? Pythagorean. Because you have the a and you have the b and you're finding the hypotenuse, the magnitude. Just reminding us. Just reminding us. But yeah, we're going to do the square root of Pythagorean theorem with these two legs. That's going to be for vector u. But how many magnitudes do I need? Both. Yeah, 2 of them. So then what's going to be my square root for v? Good. 4 squared is 16 plus 0 squared is 0. You guys are... So remember, magnitudes are found from the beginning of section, or not the beginning, the middle of section 6.3 by doing the square root of a squared plus b squared. So 3 squared is 9, 2 squared is 4. That's for vector u. And then a squared plus b squared for v. 4 squared is 16, 0 squared is 0. How do I get theta? Do you guys understand why I'm doing cosine inverse? I have to take cosine inverse of both sides, and I end up with 12 over the square root of 13 times, and the square root of 16 is just 4. I could reduce that, but we're going to our calculator anyway, because that root 13 is not a unit circle value, sadly. So in degree mode, using cosine inverse, I think Adam's up here doing it, and I hear Austin's getting his calculator out to double check. What do you have, Adam, for Austin to double check? Let me know if you get that, Austin. As I hear a few people trying to double check this, you technically could kind of eyeball it too and see if it at least somewhat makes sense. Because you could go ahead and draw vector u by going over 1 and 2 and 3 and up 2. Then you could draw vector v by going 1 and 2 and 3 and 4 and 0. I guess that looks kind of like a 30-ish. Good, good? Cool. Now, is that enough to tell us exactly what it is? No, but drawing a picture does kind of give us the idea. If we had found 150, we're in some big trouble. Since we found 33 and that looks like a 30-ish, yeah, sounds good. You all my ones on your calculators. But do you guys realize if I had given you this formula at the beginning of chapter 6, right after we've covered all those formulas in chapter 5 with all of our trig identities, the sum, the difference, cosine of a plus b is cosine a, cosine b, minus sine a, sine b. Here's another formula, use it. You would have had no clue, what? But now you know that's a dot product. These are magnitudes. We're dealing with a vector diagram. You've learned so much in chapter 6. Don't get stuck on how it gets difficult. Just keep reminding yourselves you're learning a lot, which will help you in a physics class someday, and specifically for the chapter 6 test. Okay, that's one application, angle between, how to use dot products. Here's another one. I briefly showed you on Friday, we just didn't get to practice it. How to figure whether or not figure out quickly, I should say, whether or not two vectors are orthogonal. Because if they give you vectors and components or linear combinations, without drawing a really precise diagram, who knows if they're orthogonal? Wait. Why is this word orthogonal important? Let me know when you get to what orthogonal means. What's orthogonal mean? Vectors are perpendicular, and why would that be so helpful? Right triangles, right angles, yeah. With right angles, we'll have right triangles. And we wouldn't say they're working opposite each other, because that would be like 180 degrees. One's going one direction, one's going the other direction. Gravity's trying to hold this box on the ground, and I'm trying to lift it straight up. We wouldn't say they're working opposite each other, but they are working orthogonally to each other, perpendicularly to each other. There is another word in math that kind of means this whole right angle. Perpendicular, remember? We could say at 90 degrees. At a right angle to each other. But there is technically another word. The other word, orthogonal, is one way. Perpendicular is one way. I know it's weird. There's so many different words. The other way is normal. I know that's kind of awkward. You're like, what? That's an English word. Normal means, well, what is normal? I don't know. Does anyone really know what normal is? But in math, a normal vector or a normal force, or a force that's normal, is a perpendicular one. So I know it's weird. There are a lot of different synonyms on this page. Orthogonal, perpendicular, normal. They all mean at 90 degrees or at a right angle. But if you guys notice this formula, now hold on, wait. Are you still putting your vector arrows above? If not, get those vector arrows in. Remember, these bold letters, you can't write in bold. I would hate to take off points just because you guys weren't doing your notation correctly. But without having to draw a super precise diagram, et cetera, and figure out with a protractor whether or not two forces are perpendicular or not, and still having a little bit of doubt, being like, I don't know, is it 90? I'm not really sure. We can mathematically figure out whether or not two forces are normal just by finding the dot product. And if they truly are perpendicular, the dot product will be 0, which kind of gives us an idea as to what the dot product is. But let's first go ahead and try it down here. I've given you a kind of tricky example just because, I don't know, there are a few weird things about this one. Guys, how do we even do the dot product of this guy? Don't I need to do my, like, u1 times v1, or my a of u times a of v, and then plus my u2 times v2, or my b of u times my b of v? First of all, who's my u1 of vector u? Oh, just 1. Okay, that's not a big deal. So I have 1 because it's 1i, and then a v would be negative 2 because it's negative 2i, right? So if I was to write this in components, because these are linear combinations, I would do 1 comma, and down here I would do negative 2 comma. Now this one's easy to fill in, right? But what's going on in the first one? Yeah, if there's no, it's going to be a 0. There we go. So sometimes it might be a little easier to think about writing it in components. Because if you only have an I, then the j must have been a 0. But now I have my dot product, and what happens when I multiply and add? Negative 2 plus 0 is not 0. So what do I say about these two vectors? They're not orthogonal. What are they? Well, how could we know what they are? Huh? Yeah, if they equaled 0, we would know 90 degrees. But what about the ones we've been given? We know it's not 0. So, okay, we're like, they're not orthogonal. Great, they're not 90 degrees. Well, what angle are they at? What angle are they at? What's the formula we just did? Right? Wasn't it angle between? So let's take this idea and go backwards and say, hold on, wait. Does this formula have to do with this formula? What if the dot product was 0? If the dot product was 0, then cosine, that's, let's try again. If the dot product was 0, then if we went ahead and tried to plug in, wouldn't we have 0 over who knows what? Yeah. What do we know about when cosine is equal to 0? Isn't that 90 degrees when the x is equal to 0? Oh my goodness. So is this really just another trippy? Trippy. I guess I could have just not told you this and been like, hey, guess what? Whenever you do the other formula, if it ends up being 0, but this is shortening it and being like, oh, okay, without having to think through the trig, let's just say when the dot product is 0, boom, it's 0. If the dot product is not 0, well, then this would be a number, and you would do your cosine inverse in the formula and get it. Like the last one. The last one would not have been 0. The dot product ended up being 12. Yep, not perpendicular. Why? Well, it was 33 degrees, 0.690. Okay. Let's take this idea then and go and talk about the last application, which is kind of the most complicated, but we're not going to hurt our brains too much on it. The idea of projection. Let me go ahead and zoom in. The idea of projection. In this picture, there are two different types of pairs of vectors, where theta is acute or theta is obtuse. And you might be like, okay, well, wait a minute. What if vector u is in the third quadrant? Well, if vector u was in the third quadrant, we would still say that the angle between would be obtuse if you went the negative direction, or in the fourth quadrant, acute. So either theta is acute or theta is obtuse. Either you're measuring positively or negatively. In this idea, we're talking about specifically projection, projecting u onto v. You know what? Actually, maybe. I might change this title, because we already talked about vector components, and we were specifically talking about side carets. That might get confusing. Let's just do projection instead, okay? We'll call this projection instead of vector components. You guys have some idea of the word project, right? Projection. I mean, what are you looking at right now? A projection of what? Of my computer screen through the projector, right, onto the board. It's not coming from the, not. The smartboard is a touch-sensitive screen, and so I orient it to tell the smartboard where that picture is showing up, so it translates to the computer with the touch-sensitive result of writing or dragging or clicking. But what if it didn't have to do with like an actual screen? So projecting, putting onto something else. Does that ever happen just in life? People ever heard that? Like projecting. You're projecting that on. That's the idea. You're putting something on someone else. You're having a bad day, and so you're basically projecting, putting that onto any situation, any conversation, any relationship that day. Like, wait, I didn't mean that. You're putting your issues into or onto me right now. Projecting, right? So how does that work with vectors? How does that work with vectors? I'm going to go ahead and zoom out just a little bit. Well, let me just scroll down. You guys should have gotten the pictures at the top. Let me give you this example to write down. Projection. The way I'm going to illustrate, it's kind of like the first picture, it's not the second one, but that's okay. Still the same idea. Question, what am I doing right now? Yeah, but where's the stool moving? Across the carpet. So if we were talking about the stool's motion, right? What vector would we use for the stool? Would he be on the x-axis? Would he be on the y-axis? Or would he be at an angle? The stool. The x-axis, because he's horizontal, right? But let me move the stool back just a little bit. Went too fast. What if we were talking about the force that was making it move? X-axis, y-axis, or at an angle? The same way. If it was the same way, wouldn't I have to be down here pulling it? Ah, see the difference? But I am exerting, right? I am exerting force at an angle. And what's the overall effect? Projection of what I'm working. I'm working at this angle. This is my vector, right? So I'm working here, but what's the projection of this work on the stool? There. Right? Now, question. Is this stool going to move faster if I exert this force at an angle, or if I were able to exert the exact same force directly in line? Does that make sense? Which one would make the stool move easier, faster, quicker? Force at an angle, or the exact same force in line? Right, because as soon as I'm exerting force at an angle, aren't I kind of losing some of that? Now, isn't that more practical? Why? Because how tall am I? Isn't it going to hurt me more to get down there and to do the exact same force with my arms? Whereas here, I'm pulling like with my back and with my legs, right? And we won't get into all the like, not biology, but anatomy of all that with the muscles and all that sort of stuff. But instead, just talking about, okay, even though it wouldn't necessarily be practical, and I wouldn't necessarily be able to do the exact same force if I was doing it directly in line, the idea is as soon as you go at an angle, you're going to lose some of the force as it projects onto an object. Now, up here, you can kind of see that. Up here, it's like, oh, hey, I'm dragging this little guy, and he's coming behind me. So I'm putting all this force, and it's, how is it projecting onto, or how is it working together with that lower vector? This one would be a little bit weirder, because maybe you'd be trying to pull a dog that's trying to pull the opposite direction. Oh, okay, this is a little bit harder, right? If you guys ever walked a dog and doesn't want to go with you, it could be trying to go that way, and you're trying to go this way, and how would that project? This picture is a little bit harder, though, to visualize, because it's like something's trying to go this direction, and you're pulling it that direction. So even though it's a little bit harder to visualize like a practical example as to when that could happen, it's still the idea of, okay, you have one vector projecting onto the other. What's the overall result? So let's go ahead and take this example. Let's take the formula up above and see what happens when we plug in. Okay? You guys have the formula written down? So the projection of, using the wording, that's very important, because when you have U onto V, you have to be careful because they could ask for V onto U and then everything switches. But the wording down here, do you guys see how it's the exact same as up there? So we're going to use the formula as is. And the formula says to find the projection of u onto v, I'm going to do okay, help me out guys, dot product, right? Oh, it's a great question. Let's go ahead and make u and v. I should have labeled them and I didn't, sorry. It's kind of important for our formula, right? All right, our dot product. If nothing else, you guys have been reviewing dot product today, right? It's going to be 6 times 2, true? Plus 4 times negative 3. Are we good? Double checking my work. I think it ends up with 12 minus 12. Interesting. 0. Doesn't that mean something? Is that a right angle? I'm not sure I would have figured that out on my own. I'm not sure I would have trusted that was at a right angle. Let's see what happens with the projection when we have something at a right angle. Okay, what would it be over? So we have the dot product on top, and then what's on the bottom? Magnitude of vector v squared. Okay, so let me go ahead and just get this ready to go. We're going to find it off to the side. So magnitude of v is equal to the square root of, right, a squared plus b squared, 4 plus 9. You guys agree? Okay, which would be 13. And then what do we multiply the dot product of u dot v over the magnitude of v squared times? Is it vector v? Vector v. So if you guys realize, this one's actually ending in a new vector. This one's actually ending in a new vector. This is just kind of a weird example, though, because what's 0 divided by anything? 0. And what's 0 times a vector? 0. Technically, it would be 0, 0. The 0 vector, which is a little bit awkward, I know. Because you would take your 0 and you would multiply it by the components of v, which were 2, negative 3. And you can bring a constant in, even though multiplication of vectors is weird. Multiplication by constants is easy. It'd be 0, 0. Wait a minute, then how does that make sense? In my example, and my stool was on a hill. I don't know. But pretend I was pulling it, and I was trying to pull it forwards, and I'm doing this. Is that going to work? I'm at 90 degrees. Is that going to help with that motion at all? How is this projecting and helping it move? It's not. I have to have it at an angle in order to have a projection. Does that make sense? Now, I could lift it up, but that's totally different. That would be helping in this vector, not helping in the other vector. So if I'm pulling at 90 degrees and trying to go forwards, it's not going to result in any sort of projection. Does that kind of give you an idea of projection? A little bit? Do we have another one? This kind of has to do with projection, but there's actually an easier formula. Let me go ahead and let you get down. Applying projection, and this is truly the last concept. Projection was the last new formula. The idea of work. Now that we've talked about projection and how having some force at an angle of some current movement or current motion adds or detracts, how it projects on. Now we can talk about work. Work done at an angle. Because up to this point, if you guys ever talked about work in like a physical science class, work is equal to force times distance. No big deal. Well, actually is kind of a big deal. Because what if that stool weighed 2,000 pounds and I was trying to pull it? Do you think I would move it? If the stool weighed a ton and I tried to pull it, am I going to move it? Yeah, no. No way, Jose. Now, what if I stayed here for like an hour, 2 hours, 3 hours, pulling with all my might, digging in my heels, pulling? Am I going to be sweating? I'm working so. Crazy thing. Someone could come in and be like, man, you're working hard. But technically, no distance has resulted. So guess what? My work is 0. This is where physics starts to get a little fun. You're like, you're kidding me. Like, you've been pulling on that thing and sweating the whole... I know I have, theoretically. But I've done absolutely no work. So if you were to come in and see someone doing something like that, and you're like, well, it's not moving, you could be like, well, yeah, exactly. You're wasting your time. Unless you're trying to work out. But even then, lower the weight so you could actually move it, right? Work is equal to force times distance. There has to be displacement. There has to be distance for technical work to be done, which in some ways really stinks. But in some ways, maybe the way we use the word work is not exactly the way that physics would define it. And that's okay. Sometimes you define words differently. But here's the dealio with work. If you're working at an angle, work equals force times distance is only easy when you're pulling directly in line with the movement, the motion, or the force of the object. As soon as you are exerting some sort of force, like me in the stool, at an angle, all of a sudden I can't just say my force at an angle time distance, because technically my force at an angle, like we just said, projects down here in the force that the actual formula is built on in a different way than I feel. Even though I feel all this work happening, it's only resulting in, it's being decreased in the actual movement of the object I'm trying to pull, as my example. So down here, as soon as we have forces acting at an angle, that's the situation, that's the scenario. One way of talking about it would be the magnitude of the projection vector times the magnitude of the actual distance that's moved. So one way is the magnitude of the projection times the distance, basically, the magnitude of PQ. But the other way of doing it, which actually might be easier, which is why I'm going to star it, I'm going to circle it, and I'm going to say use it, is the dot product of the force at an angle with the distance. The distance vector, I should say. So both of them end up in a value, both of them end up in a number. This first one is going to be a magnitude, which is a number, times a magnitude, which is a number. This bottom one says just take the dot product of the force vector with the distance moved vector, and you're going to get the exact same thing with a lot less work. But ultimately what that dot product is doing is projecting that force at an angle down in line with the motion in order to be able to do that force times distance that we actually need. So this example down here, if I have an object, in this case a particle, that's being moved from P to Q, which isn't a straight line, but that's okay. With this formula, I don't need it to be a straight line. Being moved from this point to that point. And the direction of the force of that movement is right here. We could do a whole picture if you really, really wanted to see what's going on, because we would have our 1 and we'd have our 1, 2, 3. And then we would have our 2, 3 and our 4, 5. So something's being moved from here to here. However, there's this vector that's actually a -2, positive 1, 2, 3, that's acting on it. But that's really hard to see because it's over here. So we would move it over here, and we would go down 1, 2, 3, and over 2. But that could be a really complicated picture to solve. Instead of worrying about the picture, maybe we could just try to plug in. So work is equal to the dot product of the force. Wait, which of these guys is the force? Vector V. So I could say, okay, from this clue, I can say that my force is -2, 3. I know it's kind of weird, but he's my force because my PQ is my distance. So how could I make this guy into a vector? Do you guys remember how to do an initial point and a final point and make it into a vector in component form? Do we do Q minus P or P minus Q? Good. Final minus initial. So what's -3 minus 1? And what's 5 minus 3? Now do we have two vectors? And now can we do a dot product? Perfect. That's all we need. So our dot product will end up being our -2 times our -4 plus R3 times R2. The nice thing about dot products is it doesn't really matter what order you go in, because multiplication is commutative and so is addition. So the work done ends up being 8 plus 6 is 14. We don't have any units because they didn't really tell us units as far as what we were doing. But the goal on work is to get a vector for how far it moved, and to figure out a vector for the force, and then do a dot product. So much easier than the whole idea of projection, which makes it a bit more complicated. Still possible, just complicated. Kiddos, we didn't get into section. Ooh, work done. Remember, the goal is to get a force vector and a distance vector. Anyway, your homework 6.4 due tomorrow, so we can grade it, we can check it. We didn't get into section 6.5. Maybe we'll do an abbreviated version of it, because that's the end of our chapter, and we're trying to finish this guy up to get a test in ASAP. So check out your calendar online, and then we'll come back and wow on 6.4 tomorrow. Bye, guys. Uh-oh, my rope is stuck. Chapel day, chapel day.